Thank you. So I wrote here a quick summary of what we did yesterday. So on top, I remind you what constitutes the model category on the omega cat. So it's defined by this set I of generating cofibrations, simply the inclusions of spheres into disks. And I gave the definition of weak equivalences. Those are maps such that if you have a zero cell in D, then there is a zero cell in C such that its image is omega equivalent to D. And in higher dimensions, if you take two parallel cells in C, sent to FC, FC prime, with a cell V in between, then you can lift V, not exactly, but again up to omega equivalence of cells. So we were trying to check the conditions that will make this data I and W model category. So this is based on Smith's theorem again. And I remember you that we have to check 4 conditions. That W has the 342 property, that I injectives are weak equivalences, that I cofibrations, remember I cofibrations, I cof is this, is stable by push-out and transfinite compositions. And then there's a solution set condition telling that whenever you have a weak equivalence here, W, and a square with I in this set I, then you can factorize this square by another square here where Ji is a set of trivial cofibrations depending on I, okay, always. So what we did yesterday is we checked the 2 first conditions for the 342, and we stopped here with this. So this is the difficult part. This was easy, and we have to check. So today we'll try to check this, and that, and hopefully go to part 2, maybe the beginning of polygraphs and such. Okay, so how do you prove this? For this, we need a construction of cylinders. I alluded it yesterday. So if you have a C in omega cat, you may define category gamma C, omega category again, of cylinders in C. I gave little pictures yesterday. Here is a quick formal definition of these objects. So it's defined by induction on n. If n equals 0, then a 0 cylinder, so somebody in gamma C 0, so it's U, and it comes with a top and a bottom, so it goes from one 0 cell to another 0 cell here. In that case, it's simply a reversible cell in C. So that's a 0 cylinder. So again, X, Y are 0 cells in C, and this is a one cell, reversible cell in C again, and that's a 0 cylinder. So this cell we call U natural, like this. Okay, and then by induction, suppose I have defined what n cylinders are. I want to define what's an n plus 1 cylinder in C. So I take two n cells in two let's say from n minus 1 to n would be easier. So let's take two n cells, x, y, in C n, and I want to define an n cylinder from x to y, like this, so certain connection. And this will be the data of two one-reversible cells. Here is one, call it U flat, and this one U sharp. Here. So it's given by two reversible cells, U flat. So this is from the zero source of x to the zero source of y. So we denote this by, again, x flat to y flat. And also U sharp here goes from x sharp to y sharp. Here. X, y, like this, plus. So remember, we defined the induction hypothesis is that we know what's an n minus 1 cylinder. So now the data is this plus an n minus 1 cylinder but not in the same category, in the category hom between x flat and y sharp. So it's an n minus 1 cylinder in this category, x flat, y sharp, and I have to say what's the top and the bottom of this cylinder. So those have to be n minus 1 cells in this category that is exactly an n cell in the original category, and this n cell is simply x. So this new cylinder U goes from x composed along a zero connection with U sharp to U flat composed with Y. Of course, those cells are seen in this category, so I should put brackets here as I explained yesterday. Okay. So it may be useful to just unfold this definition for n equals 2. So I do it only for n equals 2, and you'll understand how it goes generally. Not this one, it's this one. Yeah. Yes. And the middle one. Okay, now if you unfold this, as I said, for n equals 2, So what's a two-cylinder between two cells, X and Y? Look at the pictures. So you have X here. Okay, this goes from a cell X1, say, flat to X1 sharp, source and bottom. Okay, that's the zero source. That's the zero target here. And there's another cell here, Y, two cell. To this here. So here you have. So it appears like this. So first, by this inductive process, you define two cells here, U flat, U sharp. So those are one cells in C. And then what I want is a one cylinder U in this hom category here. So that's what's that cylinder? Now the top is this composite and the bottom is this composite here. So I have to understand what's the zero source and zero targets of these cells in the hom category. So this is simply, as for the source, it's simply X1 flat composed with U here for the, so, and the target is here, I'm lost here, okay, I have U, so you have here, sharp, yeah, here. Sharp here. So it basically boils down to the one cells, the one reversible cells that I need to build this one cylinder have to be in the original category two cells, so the front face, so one two cell, say U2 flat going from X1 flat U sharp to U flat Y1 flat again here, and the other one comes from goes from X1 sharp U sharp to U sharp to U flat Y1 sharp. So what you build is this cell here, a cell here, bottom. Okay. Two cells like this. Okay, so those two cells, those are reversible one cells in the category X, Y, like this. Okay, so reversible one cells. And now, by induction, I have to build a zero cylinder in, again, the corresponding Hom category, and this zero cylinder is in the original category, a 3-cell here. So this 3-cell I call U natural, so it's the big cell. This cell U natural goes from, so in the original category again, goes from X, okay, you have the U1 here, sharp, composed in dimension 1 with U2 sharp, and that goes to U2 flat, composed in dimension 1 with U1 flat, composed in dimension 0 to Y. Okay.
There's some dispute about whether this intervention on point is correct.
No, I don't think it is. I'm sorry. No, I don't think it is. It's a bit tricky. You have to always imagine visual as the right Hom category. So, but okay, when you unfold the definition, you get this sort of formula, and you can easily imagine how it is in dimension n. So you get the general formula for the principal cell of your n cylinder. Okay, so that's how it goes. So I don't want to bother you too much with these technicalities. I will just, so this one, yeah. So now, to make it short, what I defined are cells, certain cells. When you have a cylinder like this, from X to Y, cylinder U, from X to Y, there is the front face and the bottom face, and are themselves cylinders of one less dimensions, and those are the source and target of cylinder U. So this U goes from V, say, to W as new cylinders. And you can check that this builds a globular set. Also, you can compose cylinders. For instance, you can compose cylinders like this, or like this. This is quickly composite of two. So those are two cylinders, actually. You can compose them. And you can check that all axioms of strict omega categories are satisfied, so that gamma C defines a new omega category together with functors. So you get two projections. Pi1, pi2 over C. Those are the maps that send a cylinder here on top, here on bottom. And those two maps have a section, a common section called tau C. So this, what does this section? It simply takes an N cell, X, and builds the trivial cylinder on X, that is a cylinder 2X going from X itself to X, the vertical cells being identities, of course. So get these cylinders. So it's easy to see that these, this tau is a common section of the projections. Okay. So far so good. Why do we introduce this? The idea is again to prove the 3 for 2 in the third case, and for that we need a very important lemma on these cylinders. It's a transport lemma. Lemma of transport. What does it say? I'll explain it in pictures. It says that whenever you have two parallel cylinders, like this, for instance, okay, those are, so the one that's behind and one in front are parallel because their source and targets are those cylinders here. Okay. If you have this situation, so two cylinders, U parallel to V, let's say U prime here, so U and U prime on top. So this goes from X to X prime, this, no, X to Y, it's better. U prime goes from, say, Y to X to Y, X prime to Y prime, sorry. Okay. So this lemma says that if there is a cell V here, if there is V from X to X prime, then you can fill the whole box with a new cylinder. So then there is W from Y to Y prime and a cylinder W of top V, bottom little w. And this cylinders, in the category of cylinders, has source U and target U prime. So it goes from U to U prime, like this. And that's the first part of the lemma. Plus, this cell here, this cell W, is weakly unique, meaning that if there's another W filling the gap, then this W is automatically omega equivalent to the first one. Okay. If there is another W, if W prime, say, goes from Y to Y prime, then in that case, this W prime necessarily is omega equivalent to this W. Yes?
If you're using lax cylinders instead of ones where the vertical cells are reversible,
yes.
Is the filler still weakly unique, or does this lemma not work at all, or does it only work for one direction?
I'm not sure what you mean about that. So from lax cylinders,
we're just ordinary cylinders where the vertical cells are not reversible.
Oh no! In that case, you can't do that stuff. No. Just you. No, you really, the reversibility is really absolutely necessary in that situation. Yes, absolutely. You have to. You want to be able to just go from top to bottom in a very easy manner. So in that case, you have this, and conversely, if here, for instance, you have what I was about to say. No, I don't want to mess up here. That's my transport lemma. It's here. Okay. So yes. Okay. Yes, and again, yes, sorry. And again, if you take a cell W prime, omega equivalent to W, then there is a cylinder, a big cylinder, W prime, which is omega equivalent to W in the category of cylinders. Okay, so that's makes it very easy. So I don't want to prove this this lemma. It's quite technical, but so this is the first one. Okay, of course, this was the top-down transport lemma. Of course, you can go the other way. If you have a cell filling the bottom, then you can lift it in that sense to the top. Okay, so what is this lemma good for? First, remember that you have your gamma c, you have your projections, pi 1 c, pi 2 c over c. Both projections are trivial fibrations, belong to here. Okay. This is the see. Okay, this is an immediate consequence of the transport lemma, of course. For instance, if you take two, what does it say that it's in I right here? you take two cylinders, parallel cylinders, like this, and say the first projection here on top, here. And to check that this is a trivial fibration, you have to say that if you have a cell here, then you can lift it here. But this is exactly what the transport lemma says. So first consequence is that these maps are trivial fibrations. On the other hand, the trivial cylinder, tau, C, from C to gamma of C, this one is a weak equivalence. Tau C belongs to W. So that's, again, very easy because you get tau C, gamma of C, take a projection, for instance, pi 1 C. It's a section, so the composite is an identity on C. This is, of course, a weak equivalence. This is a trivial fibration, then also a weak equivalence. And this is a case of 342 that we already checked yesterday. Okay, so it's not, have to be careful. So tau C here is in W. So that's it's nice. What should I do? Maybe. C. Let's see. Now we're slowly approaching the resolutions of this difficult case. A small construction, the mapping space factorization. Suppose you have map F here in omega cat, and you take this projection here, pi 1 d from gamma d to d. Take the pullback in omega cat of those two maps here. Here, where's my thing here? 1, 2, yes. Okay, so what are the cells here? There are, of course, pairs of cells. In pi f, you take an n cell of C, C for instance, C, an n cell, and a cylinder, n cylinder in D, say U, and this cylinder has a pi 1 that goes in FC. So the top is FC, and the bottom is any n cell D in D. So those are the cells here. Now, if you consider this diagram here, so here's the identity. I put F here, okay, over D. Here I have my tau D inclusion. The pullback property gives you here a certain map F tilde. Okay. And I define F hat to be from pi f to d to be the composite of pi 1 d with this f prime. F prime. Okay, so that's F hat. And the small remark is that F factorizes as F hat composed with F tilde. F tilde. Okay, that's this small construction here. F hat. Oh, it's not pi 1. I'm sorry, it's pi 2 here. Pi 2 here, of course. Otherwise, it has no interest. Okay, that's pi 2. So what does this F hat? It takes a cell like this and outputs the cell D here in D. Okay. Now this is easy to understand. You take a cell C in C. F tilde gives you the trivial cylinder between FC and FC, and pi 2 goes to FC. So you have this. So what's the point of considering this F hat? Is the following proposition. F is a weak equivalence if and only if F hat is an I injective, is a trivial vibration. So this is really interesting because it's difficult to deal with weak equivalences because of these omega equivalent relations, whereas trivial vibrations have strict lifting properties, much more easy. Okay, maybe I could Okay, so how goes that? So in one direction, it's very easy because if F is a trivial vibration, as this one is a weak equivalence, then yes, of course, that's again the this property. No, it isn't. It isn't. Let's see. How's that? F. Where am I? F is in double. Yes, exactly. That's what I mean. Thank you. Yes, this here is a pullback square. So this map here is a pullback of a trivial vibration so also a trivial vibration. So this is a weak equivalence. This, of course, is one, and then this case has been checked. So this F is a weak equivalence. Okay, that's good. Is a weak equivalence. Conversely, if suppose suppose F in W, you want to prove that this is a trivial vibration, and this will come again from the transport lemma. Okay. Why? You. Where's me? Yeah. You have consider F hat here, so that goes over D, and to check that it is trivial vibration, you take two parallel cells, so C, a certain cylinder from FC to D, and a parallel cell, C prime, U prime, FC prime to D prime. And you go here to D by F hat, so that's simply D and D prime, and so you suppose that you have a certain cell, say Y from FC, no, it's not good. No, Z, you have Z from D to D prime, yeah? And you apply the transport lemma that gives you a cell between C and C prime, between, FC and FC prime, and two parallel cylinders here, and a cylinder here going from U to U prime. Okay? And the fact that F is a weak equivalence gives you a cell between C and C prime. Okay? That goes to, by F, to something that's omega equivalent to Z. So that's another application of this transport lemma. So given this property, we are finally ready to state the last bit here. Okay. So I'll do it in pictures again. So the picture is like this. I did a small picture. So now I want to prove that if I have this triangle here and H and F are weak equivalences, so is G. So it goes like this. You have a C here, C, D, E, say, so F, G, and the composite H here. Okay. You start with two cells here, two parallel cells, D, D prime, D, D prime, that are sent by G to here, GD prime, by hypothesis, you have a cell here in between. I call it W, for instance. W. Okay. Okay, now, F factorizes through this F hat here. And I know that F is in W, so that F hat is a trivial vibration. Okay. As F hat is a trivial vibration, there are cells here, C prime, C prime, and the cylinder here, not one cylinder, two parallel cylinders here, one from FC to D, the other one from FC prime to D prime. So that's only because this pair here lives here. So the pair C with the cylinder, C prime with the cylinder, those two pairs live here. And those are the two parallel cells that are sent by F hat to D prime. Okay, so that's the picture. So once you get this cylinder here, you apply G, and you get another pair of cylinders here. This. So this will be HC prime here. But now H itself is a trivial vibration. Okay, so you have pi H is here, okay, like this. H itself is a trivial vibration, so that gives you cell. So yes, it trivial vibration. So yeah, that gives you finally an X here between C and C prime. Why is that? I think you should. Sorry, I'm a bit lost here. W G prime.
Isn't that the transport lemma?
Yes, it's again the transport lemma. You have to use transport lemma. I'm sorry, I'm missing something here. Excuse me? Yes, you can transport W on top here, and then you lift it here. Okay, yeah, sorry, thank you. You lift it here, and then it comes here. Okay, comes here. And well, I leave the details, the checking to you. I'm going to take too much time here. So remember, what was really difficult is to find something here. So once you get this cell here, then you get finally a cell here. And again, by the transport lemma, you eventually come to a cell between D and D prime. And it's a matter of, well, it's easy to check that the image by G under G of this cell here is omega equivalent to the original W. So it's a bit messy, but it works. So finally, this is checked. Okay. This is good. Okay, so let's tackle the third point here. ICOF intersection with W is stable at push-out and transfinite compositions. I don't want to detail this composition. This is rather formal and has no, it's not really interesting and has no, whereas the stability by push-out is, of course, not trivial, because ICOF is formally stable by push-out, but W isn't. Okay, W isn't. So the strategy to prove this is to define a new class Z of morphisms, such that all trivial cofibrations belong to this class, and all members of Z belong to W, and Z itself is stable by push-out. Will be stable by push-out. I won't have the time to give all details about this construction. I still define Z. So in our case, the choice of Z will be immersions. So what's Z? You say that a certain map from C to D, F, belongs to Z if first there is a retraction, G. So first you ask JF is identity on C, and there's a map H here from D to the cylinders on D, such that pi 1 D H gives you, I don't, pi 1, in which sense I don't want to mess up because you have two possible directions. Two possible directions. Where is that? Let's get back. This here. Okay, so pi, the first projection is F composed with G, and the second projection is simply the identity on D. The identity on D. And also there's another condition. You ask H to be trivial on the image of F, meaning that H composed with F is the same as H composed with H composed with HFX is tau F. It's tau F. Tau dF. Meaning that it looks like this. Okay, so this so these maps are defined by equations. So it's quite easy to show that Z is stable by push out. Okay. It's really annoying. I had notes somewhere. So what does this Z here? It see D here. Okay, set point here. F, and if you have a certain D here, so H of D goes like this. Okay, you can picture this in that direction. So this is stable by push out. The fact that I cof inter W is in Z. I was sure. Check this. Sorry, I'm a bit lost here in my notes. Oh, here it is. Yeah. Sorry. There it is. Okay, so you may characterize maps in Z as follows. You have this picture here, pi f, okay, f hat here, and you have the projections like this. C and here. Gamma D. Okay. So you can check that the fact that F is in Z boils down to the fact that this diagram has a lift here, K. Here. Has a lift. So this is projection, the first projection of the pullback. Yeah, it's still over there. Okay, it's the map on top. So if there is a lift here, then you can build a retraction for F. The lifting goes like this. The retraction is simply this composite here. Okay, so you go to pi f and you project over C. That gives you G. Here, it's G. Here. And H is the other composite here. That gives you H here. Okay. So if there's a lift, then you get those two maps, J and H, and it's straightforward to check that the condition of emergence are satisfied. And well, conversely, it's not much more difficult. So what is this good for? Push out. Yes, you want to check that iCof is in Z, but now if F is a trivial cofibration, then in particular it's a weak equivalence. And we saw that in case of weak equivalences, F hat is a trivial fibration. So you get a lift K here. Okay? So that's how it goes. So this is good. Okay. And the fact that Z is in W, that comes from, okay, say you have a map in Z, an immersion here, immersion here, that must be one case of 3 for 2 around here, okay? So that's set. So condition, so we checked this, that, and that. Now, a quick review about now, as for the solution set, I just described the construction of this JI without proving much. Okay, solution set. You have your IN. ON to ON here. And these maps fit into a push-out diagram like this. When you push out 2 copies of ONs along the common border here, delta ON, then what you get exactly here is the next sphere, delta ON plus 1 here. So that's a push-out. That's a push-out. Okay. So how are you going to build this J here? Again, in this case, JI is simply one map. It's a single map. It goes like this. This push out here, if you, sorry. Of course, if you send these to ON by identities, then there's a single map here called ON. It's a map that flattens the sphere on a common hemisphere. Okay, so this map here. ON. And here the small object argument allows you to factorize this map by cofibration followed by a trivial fibration here. And here you get a certain object, Pn, here. So this is called Kn, say, and this is Pn here. So this is a trivial fibration, this is a co-fibration. And now, if you compose, so delta 1 goes to Pn, if you compose with those maps here, you have, I don't know how you call it, I don't know, V here, or source and target if you want, source and target. If you compose Kn with source and target, then you get maps. For instance, you get a map Jn from On to Pn. Jn is here Kn U. And all the same you get J prime N On to Pn. J prime N is Kn. No, that's not U. S. S and T. In pictures, what you do is, in dimension 1, for instance, you P, this is P1, okay. So P1 has two parallel cells like this, and a huge amount of cells, of reversible cells in between, ensuring that this becomes omega equivalent to this. Okay, so that's the idea. So that's the map PI, and this Jn is the unique member of the solution set. Okay, and so now what we have is a square like this. You have delta. You have your In here, your In, On, another copy of On, and you get Jn here over Pn, and here J prime N. Now, as for the solution set, this square here is exactly this one that we were looking for. Okay, so I'm not going to too much details about that, only one little thing. So what you get is this. Suppose you have a square, commutative square, with F a weak equivalence here. Then this simply means that, so what's the map from delta On to C is just a pair of parallel cells, C prime if you want. And this is simply a cell, say, U in D, and U goes from C to C prime. Okay, but now, excuse me, FC to FC prime. Thank you. FC to FC prime. Now, if F is a weak equivalence, then there's a cell V between C and C prime, such that FV is equivalent, omega equivalent to U. So that means that you can put here your square Jn in such a way that the diagram commutes. Okay, maybe I didn't say something important. Yeah, something very important is that Jn is a trivial cofibration. Okay, is an ICOF W Jn. So that's quite easy to check from the conditions. So yeah.
Have you given have you ever explicitly written out what Jn is in terms of a polygraph?
No, I never. I never. Of course, this Pn will be a polygraph. Okay, I'll explain that in a minute. Starting, would like to start a little bit of part 2. Otherwise, I'll be really trailing my schedule. The explicit description of Pn is not really something easy. See, there's lots and lots of cells, and the choice is not unique, of course. Okay, so there are many solutions, but all of them are polygraphs. That's for sure. Okay, that's really an important point. So that's what closes part 1. So in the
perhaps before starting part 2, you can give the reference of this.
Yes. So, yeah. Thank you. I missed that. I thought about it in the beginning, and then no. The reference is the paper "A Folk Model Structure on Omega Cat" by Yves Lafont. Christoph Voritkiewicz, I think that's it, and myself. Okay, and it's in paper of 2010 in Advances in Math. So all proofs are detailed in this in this paper. Okay, so just a quick introduction to part 2. That will be about cofibrant objects in this situation, in this model category, cofibrant objects and polygraphs. And polygraphs. Just a matter of terminology. Just a polygraph is a computer, okay? So polygraphs that appear in streets work much earlier under the name of computer, but then for several reasons we adopted this terminology, but it's exactly the same, so it's not, there's no discussion about that. Okay, if you have consider this this picture, you have the category of you have cat n categories. So all I said here may be truncated at dimension n. I systematically consider cat n as included in omega cat in a natural way. So if you take a category up to dimension n, then you can always add identity cells in higher dimensions to get an omega category. So I will not, I'm not really careful about that. You get a forgetful functor to globular sets, to n globular sets, glob n. And here there's a truncation functor from glob n plus 1 to glob n. It's simply forgetting the n plus 1 cells. And in cat, you can take the pullback of this diagram. It gives you a category I call cat n plus. So what's cat n plus? An object of cat n plus is simply an n category, C, together with a set S of cells, set of n plus 1 cells attached to C by source and target maps. Okay, so this, let's call it Sn plus 1. So the picture is, what you have is a pair of maps from S plus 1 to Cn. So that would be Sn, source n, and target n. Source and target. So you basically attach a cell on a pair of already existing parallel cells in Cn. Now, if you take here cat n plus 1, this square commutes, forgetful functor, truncation here, and you get a functor W taking an n plus 1 category to an object of this 1 here. What it does, it does nothing in dimension up to n, and in dimension n plus 1, it takes a cell to itself, but simply forgets the compositions and identities, so it forgets the algebraic structure on the category. Okay, so this functor happens to have a left adjoint here, L, meaning that you can build the free, if you take an object here, C+, in this category here, you can build the free n+1 category on C+, okay, L of C+. Intuitively, what you do is you take your cells in Sn+1 and you compose them freely using the axioms of n+1 categories. So if you repeat this starting with dimension 0, you get the following picture. You have a set P0 of 0 cells, so that's just a set. There nothing happens, so you generate freely the same object, so that's the identity, of course. And then in cat 0, which is set plus, you take simply a set P1 of 1 cells with source and target, S1, T1, like this. Okay. And the functor L produces one category, like this, and so on. So you attach 2 cells over P1 star. You apply your functor L to this object here. This object here is in cat 1 plus. Okay, so you apply L. This vertical map is simply the unit of the adjunction. Okay, it's the insertion of generators. Simply, so you get P2 star and so on. So this process, the object you built by this infinite process is a polygraph. Okay, so Pol omega, the category of polygraph, is the category whose objects are these diagrams here with all conditions, and morphisms send generators to generators. So it's a very rigid notion of morphism. So that's the category polygraph. Once you have a polygraph, it comes immediately on this line with an omega category. So if you have P, then you can attach to P star, so the free category generated on this polygraph here. Cat omega. That's a quick view of what a polygraph looks like. Okay. Yes. Now, no. This won't do. The situation and I finish with today with this proposition. proposition, polygraphs are cofibrant in omega cat. So one sense, polygraphs, well, not polygraphs, sorry, more precisely, categories of the form P stars were freely generated by polygraphs. So if C is of the form P star, P in polygraphs, then C is cofibrant, meaning that the unique map from the initial category empty to C is a cofibration. So why is that? It's easy to understand, because how you build these objects? You build these objects by freely adding cells on a base in a repetitive way. The step of adding cells on an n category looks like this. To add cells, you have your n category here. To add a certain set of cells, a certain S plus 1 of cells, you have to choose pairs of parallel cells here. So basically what you have is a map from delta O n plus 1 to C here. Okay, so that's a map alpha, say. Okay, and to add cells to get to the next level, you push out by this O n here as n plus 1. So you have a push out here. Okay, C alpha. Now, remember the INs are, so this is of course, the co-product of the INs. So the INs are cofibrations. Cofibrations are stable by sums. So this is a cofibrations. Those are stable by push-out. So this is also a cofibration. And if you build polygraphs as I showed you by stages, then what you get is a sequence of freely generated n categories starting with C0, then it injects in C1, etc. Okay, at the co-limit, you get your category P star like this. Okay, I should have written P, it's better. It's more consistent. And now, all these maps, because of that, are cofibrations, and so is the countable composite of those maps. So here, of course, if you start with 0, this is a cofibration, and your polygraph is cofibrant. Okay, so you have cofibrant. Not only that, but polygraphs can serve as cofibrant replacement in omega cat. Why is that? Just because we saw that there's a functor from polygraph to cat omega here. This is the left adjoint, the free functor. This functor has a right adjoint, starting with a polygraph here, with a category and giving a polygraph. So what you get is a monad on polygraphs, yeah? T. And it happens that the co-unit of this monad, So you take C, and you take this functor I'll call perhaps P, like this. You take P of C, you take the free category of P, you get your co-unit here. So it happens that this epsilon C belongs to ING. It's a trivial fibration. So I think I'll finish here. I'm running late. So sorry.